Hello, math enthusiasts and curious minds. Today we're diving into one of the most misunderstood results in mathematics, the claim that the sum of all positive integers equals -1/12. Let's explore what this really means and clear up some common misconceptions. First, it's crucial to understand that in the conventional sense of summation, the series 1 plus 2 plus 3 plus 4 plus so on does not equal -1/12. This series clearly diverges to infinity in standard calculus. Next, we show how to solve this issue from another perspective. Let's start with something simpler. Consider the infinite sum, s equals 1 minus 1 plus 1 minus 1 plus 1 minus 1. And so on, continuing infinitely. This is known as Grandis series. It doesn't converge to a single value in the traditional sense. It oscillates between 0 and 1 depending on where you stop. We can assign it a value of 1/2 using two different methods. Method 1, series manipulation. Let's call this sum s equals 1 minus 1 plus 1 minus 1 plus. If we subtract 1 from both sides, S1 equals -1 plus 1 minus 1 plus equals 1 minus 1 plus 1. This gives us S1 equals S, which means 2 seconds equals 1. So S equals 1, 2. Method 2, power series approach. We can view this as related to the geometric series 1 divided by quantity 1 minus x equals 1 plus x squared plus x cubed plus ... which converges when the absolute value of x is less than 1. If we substitute x equals -1 outside the convergence radius, we get 1 divided by quantity 1 minus -1 equals 1 divided by quantity 1 plus 1 equals 1/2 equals 1 minus 1 plus 1 minus 1 plus ... While this formal manipulation isn't rigorous in standard calculus, it gives us the same value s equals 1/2 that other regularization methods produce. This approach connects our series to the analytic continuation of the geometric series. Now, let's look at the series we're interested in. S equals 1 plus 2 plus 3 plus 4, and so on. Whatever the sum of the series might be, call it C equals 1 plus 2 plus 3 plus 4, and so on. Then multiply this equation by 4 and subtract the second equation from the first. This gives us -3c equals 1 minus 2 plus 3 minus 4 plus 5 minus 6, and so on. The key insight is that the alternating series 1 minus 2 plus 3 minus 4, and so on is the formal power series expansion for x at point 0 of the function 1 divided by 1 plus x squared, which is 1 minus 2x plus 3x squared minus 4x cubed, and so on, evaluated with x defined as 1. Accordingly, we can write -3c equals 1 minus 2 plus 3 minus 4, and so on equals 1 divided by 1 plus 1 squared equals 1/4. C equals 1 plus 2 plus 3, and so on equals -1/12. This is where the famous result comes from. However, it's critical to understand that this is not a standard summation. This value comes from the Riemann zeta function zeta s through analytic continuation. The Riemann zeta function is defined as zeta s equals 1 plus 1 divided by 2 to the power of s plus 1 divided by 3 to the power of s plus 1 divided by 4 to the power of s, and so on. For s greater than 1, this converges to a finite value. For other values of s, including s equals -1, we use analytic continuation to extend the function. When s equals -1, we get zeta -1 equals -1/12. So when mathematicians or physicists say 1 plus 2 plus 3 plus 4, and so on equals -1/12, they're using shorthand for the analytically continued value of the Riemann zeta function at s equals -1 is -1/12. This result has legitimate applications in quantum field theory and string theory, where regularization techniques are used to extract finite values from infinite expressions. But it's important to remember that in the conventional sense of addition, 1 plus 2 plus 3 plus 4, and so on is simply divergent.